Okay, anyway, we are talking about frequency modulation. Okay, we are talking about frequency modulation, and uh, we know that frequency modulation is a nonlinear technique, nonlinear CW modulation technique. Okay, and so we have several properties related with the uh, nonlinear modulation. Okay, the message spectrum is directly related with the modulated spectrum. Okay, and the modulated bandwidth is or transmission bandwidth is very much greater than twice the message bandwidth, and SNR can be improved without increasing TX power, transmission power. Okay, so those are the properties of nonlinear modulation. Okay, okay, so so I have already uploaded the phase modulation. Okay, so there I have explained that. Okay, so you know that what is AM means. Okay, the AM means carrier signal amplitude, carrier signal amplitude. Okay, carrier signal amplitude. Okay, carrier signal amplitude is changing with respect to information signal amplitude. Information signal amplitude. Okay, so if I write it, A means carrier signal amplitude. Okay, in AM modulation, we are changing the carrier signal amplitude. Okay, changing here, changing the carrier signal amplitude with respect to message signal level, message signal level of amplitude. Okay, and in that is AM. Okay, so in phase modulation, in PM, we are changing carrier signal phase with respect to message signal level. Okay, and FM, in FM, we are changing carrier signal frequency, carrier signal frequency with respect to message signal level. Okay, so that is FM. Okay, so in FM means so FM means we are changing carrier signal frequency. Okay? Here it is frequency with respect to message signal or information signal or maybe the baseband signal levels. Okay. Okay. So this is the frequency modulation. Okay. So you can see that if we are changing the carrier signal frequency with respect to the message signal, okay, the frequency is changing. Okay, so in FM signal, the frequency is changing. Frequency is changing. Okay, frequency is changing. Actually, if you have gone through the PM, okay, PM also actually the frequency is changing. Okay, we are changing the phase, but again the frequency also will be changing. Okay, Okay, and amplitude FM also, the frequency is changed. Okay, so in FM, okay, in FM, so frequency is changing means the instantaneously at every instance the frequency is changed. Okay, so we can get a expression for instantaneous frequency. Instantaneous frequency of FM signal, okay, we can define as FT. Okay, so this is the instantaneous frequency is equal to, actually we put this mark also. This means by definition. Okay, this means by definition. Okay, by definition, this delta mark emphasize that by definition. Okay, so if T the frequency, instantaneous frequency of FM signal, frequency modulated signal, is equal to FC carrier frequency plus F delta XT. Okay, by definition. Okay, and this F delta T we referred as frequency deviation. Frequency deviation. Okay, deviation. Okay, actually in phase modulation also, we can I have told you that in phase modulation also sometime actually change in the frequency of the signal again. Okay, so for the phase modulation also, this is for FM. Okay, phase modulation also there is instantaneous, this is PM. Okay, instantaneous frequency. Okay, that is defined as FC plus 1/2 5 XT. Okay, so this is the phase deviation. This is referred as phase deviation. Okay, deviation. Okay, so this is the instantaneous frequency, and this is the instantaneous frequency of the phase modulated signal, and this is the instantaneous frequency of the frequency modulated signal. Okay, now we are focusing on this one. Okay. Now our focus on in this one. Okay, and actually the phase also changing. Okay, the phase also changing. Actually in phase modulation it is saying that phase is changing. Okay, carrier signal phase is changing in according to the signal amplitude, message signal amplitude. Okay, so the phase is changing means the phase is changing in phase modulation. By definition, phase is changing. Okay, but in frequency modulation also, phase is changing. Okay, due to the frequency change. Okay, so that phase, so instantaneous phase you can define as, actually it is somewhat complex. Okay, lambda d. So there is integration actually. Okay, so this integration should be T. Okay, should be T. Actually, you have to do this integration by time domain. Okay, so that is why it is mentioned like this T. So it is expressed like this to avoid the confusion between this lambda and maybe your signal also, maybe the T components are there. Okay, so in order to avoid this confusion, this notation used. Okay, and this is the phase for the frequency modulated signal. Okay, actually we are changing this one. Okay, actually in phase frequency modulation also we are changing the phase. Okay, we are changing the phase, you can see it. Okay, I will tell you. Okay, and for a phase modulation, okay, so you have the video is uploaded. Okay, in phase modulation the instantaneous phase is defined as phase deviation times xt. Okay, so his phase deviation time xt, but here the frequency deviation times integral of the xt signal with respect to t. Okay, so that is the difference between the phase modulation and frequency modulation. Okay, so you can see that in mathematical point of view, phase modulation is more complex. Sorry, frequency modulation is more complex because the integral also associated with the signal. Okay, and by comparing these two, in mathematical point of view, the phase modulation is somewhat simple. Okay. Okay. And okay, so we are now talking about the phase modulation. Okay, so we will so if you consider this frequency deviation, so uh, that is included in both instantaneous frequencies and instantaneous phase also. Okay, this frequency deviation. Okay, this frequency deviation actually, this f delta, this is the frequency deviation. Okay, this is the frequency deviation. Okay. Actually this frequency deviation is defined the shift. Okay, frequency shift of the carrier signal, shift of the modulated signal. Okay, modulated signal. Okay. So you can see it. Okay, so normally, okay, so if you consider this one, okay, instantaneous frequency definition. Okay, so I will get the instantaneous frequency. Okay, instantaneous frequency for FM signal, modulated frequency modulated signal. It is defined as FC plus F delta XT. Okay, so it is defined like this. Okay, so you can see that this XT is the amplitude level, no? The amplitude or the level of the message signal. Okay, so XT is the time domain signal. Okay, so time domain signal means it shows us the amplitude variation or the magnitude, the voltage variation. Okay, with respect to time. Okay, so this xt is a voltage value, the amplitude value. This xt is the amplitude value. Okay, so you can see that amplitude value can be a plus value or minus value. Amplitude value can be a plus value or minus value. Okay, and here according to this identity equation, you can see that if this f delta is high. Okay, this delta is high. Okay, if you get the minus value, okay, if you get the minus amplitude value at the in the case of getting a minus amplitude value, okay, there is a possibility, okay, that this fc minus, okay, fc minus, then this xt is minus value. Okay, ft minus f delta xt can be a minus value, no? can be a minus value. Okay. For example, let's say that our FC is 200 hertz, 200 kilohertz. Okay. 200 megahertz. Okay. And if delta is 10, delta is 100, let's say that 100. Okay. At that instance, okay, let's say that xt the t is at maybe at 5 seconds. Okay. This is the 5 second. Okay. So it is minus 5. Okay. So this xt will be minus 5. Okay. So it will be 200 plus 100 into minus 5. Okay. So that means you will get minus 300 value. Okay. So this FC is a minus value. Okay. But this frequency cannot be a minus value. Okay. So this F delta, okay, F delta define the frequency shift actually. How much this instantaneous frequency shift from the carrier signal. Okay, so that is why I explain it as a it is a it determine the frequency shift of the modulated signal. Okay, I think you could understand that one. Okay, okay. Now you can see that. Okay, this to avoid this situation, this type of situation. Okay, if we keep this deviation very low. Okay, if we keep this deviation very low, for example, if this deviation is 0.01 or something. Okay, so here it will not a minus value, no, it will be a plus value. Okay, so if we keep this frequency deviation as much as possible, low as much as possible, then it will not be a problem, no? Okay, so normally, okay, it is defined that this F delta cannot be greater than the carrier frequency. Okay, so this is a condition. Okay, this is a condition. If delta, the frequency deviation should be greater than the carrier frequency. Okay, to avoid this minus frequency value. Okay, and so this is the upper value, no? This is the maximum value, and we call this as upper bound. Okay, this is the upper bound for F delta. Okay, this upper bound for F delta. That means this F delta can get a maximum value FC. Okay, but normally this F delta should be very much less than the FC. Okay. For example, if FC is 200 and if delta is 150, okay, so it satisfies the upper bound, okay, it satisfies the upper bound, but maybe your modulation will not be okay, okay. Actually, due to this reason, okay, actually this F delta should be very much greater than FC, okay. We need to fulfill this requirement to keep the modulated signal in pass band. Okay, in pass band, or to keep the pass band properties of the modulated signal. Okay, so normally F delta should be very much greater than the FC. Okay, so so here what you have to understand. Okay, so this is the instantaneous frequency of the modulated signal, frequency modulated signal, and this F delta is the frequency deviation, and frequency deviation should satisfy this upper bound, okay, to avoid the minus frequency, and it should be very much lower than the carrier frequency to keep the modulated signal in passband. Okay, that's understanding is enough. Okay. Okay, now so that is it. Okay, so So, okay. Actually, phase modulated signal, okay, phase modulated signal. So that means here you have the modulator, okay, so this is the phase modulator, and you have a, message signal, MT, okay, and you have a carrier signal, XCT, okay, that is normally equal to AC cos 25 FCT, okay, like this, okay, so 25 FCT, let's write as omega CT for simplicity, okay, and the phase modulated signal we can write as, okay, so please refer the lecture, okay, we can write the phase modulated signal as AC cos omega C T plus what is the instantaneous phase plus instantaneous phase, this one. No, instantaneous phase is this one, no? For phase modulation, this is the instantaneous phase, okay? 5 delta xt, okay? So you can write it as 5 delta xt, okay? So in this way, you can write the phase modulated signal, okay? So you can see that you are changing the phase, okay? So this is the phase. This is the phase, okay? And using the phasor diagram, okay? So I think you know how to draw the phasor diagram for signals, okay? Anyhow, I have explained it in the PM lecture. You can refer that one, okay? So using the phasor diagram, you can interpret that this also will create a frequency change, okay? This phase change also lead to a frequency change, okay? So that is why it has a, in a phase modulated signal also, the frequency of the modulated signal is changing time to time, okay? So this is it, okay? And for the AM modulation, okay, sorry, for the FM modulation, frequency modulation, okay, frequency modulation, if we have a signal, so this is MT, okay, this is MT, okay, if we have a modulating signal MT, and if you are using the carrier signal XCT, AC cos omega CT like this, okay, then then you will have the modulated signal like this, okay? So that is AC cos omega CT plus, here also you are changing the phase actually, okay? That is why I called you that in FM also we are changing the phase, but in different manner, okay? That is, we are associating the integral in it, okay? So this is the instantaneous phase actually, okay? We are associate this one with the phase, okay? So we can generate a frequency modulated signal, okay? So it is as 2 f delta integration x lambda d lambda, okay? So this x lambda, sorry, this is m, okay? This is m lambda d lambda. So this m lambda is actually m lambda is nothing but mt, okay? Only you are transfer this t to lambda, okay? So that is the things, okay? With respect, instead of this t, you are using lambda here, okay? So it is m lambda in t, okay? So actually this is the modulated FM modulated signal, okay? I will write it here clearly. XCT is equal to AC cos omega CT plus 2 delta m lambda d lambda, okay? So this is the frequency modulated signal, okay? And you can see that this is somewhat complex waveform, no? Because the because the integral is also associated with the waveform, okay? So anyhow, you can see that here also we are changing the phase, no? We are changing the phase, but in some manner, okay? And this will create a modulated, the frequency modulated signal, okay? So this is the waveform for frequency modulated signal, okay? And you can see that if we are going to find the spectrum, okay? So it will be very complex, okay? It will be very complex, okay? So normally we will find the spectrum for narrow band, what is called narrow band frequency modulation. Okay, I will explain why we called it narrow band frequency modulation, and also for single tone. Okay, so normally we are going to find the frequency spectrum of narrow band frequency modulated signal for one tone. Okay, so otherwise it will be very complex. Okay, so in order to reduce the complexity, we are assuming this narrow band assumption. I will tell you what is that one, and you have to consider the modulation for single tone. Okay, so then we can try to find a spectrum, the frequency spectrum of the frequency modulated signal. Okay, uh, I will explain it and I will upload it later. Okay, uh, and to find the spectrum, actually we have another approach. Okay, using the Bessel function also we can find the spectrum. Okay, so anyhow I will upload how to find this frequency domain analysis. Okay, so I think using the Bessel function it may be easy. Okay, so maybe we can use this method. Okay, I will explain it and I will upload the lecture. Okay, so anyhow, up to now you have to understand this is the modulated waveform. Okay, so if I give you a exercise, okay, example. Okay, so your carrier signal is, let's say that your carrier signal is 100 cos 5000 t. Okay, 100 cos 5000 t, and your message signal is 2 sine 50t. Okay, 2 sine 50t. Okay, and you are asked to find the modulated frequency modulated waveform here. Okay, so can you give, and also it is given that the frequency deviation is maybe 10. Okay, the frequency deviation is 10. Okay, now you are asked to find the frequency modulated signal at the output. Okay, so try to find this as a homework. Okay, so try to do this as a homework. Okay, I will explain, then I will upload the lecture related with the frequency domain analysis of the frequency modulated signal. Okay, so I think that will be enough. Okay, so I think we have covered now amplitude modulation. Okay, DSB, SSB. Okay, and PM also I have uploaded the lecture, time domain analysis and frequency domain analysis. Okay, and this frequency modulation also, I think time domain analysis is enough, and we have to do the frequency domain analysis. Okay, and I will upload that one. Okay, maybe this frequency domain analysis, maybe we are using the Bessel function approach. Okay, So I think it will be easy. Okay. So anyhow, we will do that one also in next week. Okay. Not no need to wait until next week. Okay. So I will upload it very quickly. Okay. Within 2 or 3 days. Okay. Then you have to go through the all lectures. Okay. All lectures, the AM, DSB, SSB, phase modulation and FM. Okay. Then if you have any problem, you can ask from next week. Okay. So from next week, after discuss our issues relating with this one, we will wind up the session. Okay. So I think you got it. Okay. So please go through the lectures. Okay. So there should be, okay. So I think there should be 3 lectures, 2 lectures in amplitude modulation, and 1 lecture should be from DSB, SSB. Okay. And another 2 or 3 lecture related with the phase modulation, and 2 lecture related with the frequency modulation. Okay. Then altogether 2, 1, 3, 6, 8. Okay. So 8 lectures are there. Okay. So try to go through the 8 lectures. Okay. So it is around 16 hours. Okay. 1 lecture is around 2 hours. Okay. So if you could go through this lecture before the next week, we can discuss all the issues related with this. Okay. If you couldn't understand any point, you can ask me. Okay. Or if you haven't time, if you don't have much time to go through all this lecture, okay. If you find any difficulty to understand or something, you can ask me anytime. Okay. Okay, so we will meet in next week. I think tomorrow also we have a physical session now. Okay, so we will try to do some example related with this frequency modulation time domain analysis. And if we have time, we will try to do some frequency domain analysis also. Okay. Okay, so we will wind up. Do you have any problem? මොන හරි තියනවා නම් අහන්න.